In this example, you're asked to determine whether the columns of this 2 by 3 matrix right here span R2. So I want to go over a few things at the outset here. So first of all, R2 describes all two-component vectors, where the components, let's call them A and B here, are real numbers. Where A and B are real numbers. Okay, so that's what we're talking about when we write R2, like this here. Another thing that I want to go over, and maybe I should have used a different color here, is this concept of span. So the columns of this matrix span R2 if any vector in R2 can be written as a linear combination of these three columns. So there's a lot of really important vocabulary in this section. Each term that I talk about, then I have to back up and talk about another term. So I said that the columns here span R2 if any vector in R2 can be written as a linear combination of these columns. So a linear combination is when we take some scalar, let's call it C1, times the first column, -2, 6, plus some scalar, let's say C2, times the second column, plus some scalar, let's call it C3. So it's just some number times the first column, plus some number times the second column, plus some number times the third column. So this is what's meant by a linear combination of the columns, as a number times each column, and then you add them together. And so the columns here span R2 if we can take any vector AB that came from R2 and write it as a linear combination of these three columns. So now I've written this as a vector equation. This is equivalent to, we could express this system also as an augmented matrix. So this is equivalent to the augmented matrix where the columns are -2, 6, 3, -9, 1, -3. So we're back to this original matrix here, times the column vector C1, C2, C3 equals our just generic vector in R2, which I'm calling AB. So the columns of this matrix span R2 if this equation right here has a solution for any value of A and any value of B. So that's the question. If we're determining whether the columns span R2, then I've rephrased that now as asking the question, does this equation right here, so this is a matrix equation, isn't it? Not an augmented matrix. Here, I'll cross that off. I guess I changed plan partway through there. Okay. But so the columns span R2 if this matrix equation has a solution. So does this matrix equation have a solution for all values of A and B? The actual mathematics of answering this question is going to be no big deal, but it's understanding the layers upon layers of vocabulary that we've built in here and understanding why the mathematics says what we're going to claim. Okay, so this is the question. Does this equation here have a solution no matter what the value of A and the value of B are? So now I'll change that to an augmented matrix. I guess so I'll write that here. So -2, space that out a little better. -2, 3, 1, 6, -9, -3, augmented with A and B. And this is where A and B may be any real numbers. Okay, so I want to row reduce this and see what the solution set looks like. Rather than get a 1 in this position, remember that your pivots don't have to be 1s. And so since I see this, what I have here in row 2 is just an integer multiple of what I have in row 1, I would focus on zeroing out this entry in row 2 rather than focusing on making this a 1 in the corner. Because pivots don't have to be ones. Pivot by definition, first non-zero entry. So it just has to be non-zero. Okay, so anyway, I would want to do the row operation 3 row 1 plus row 2. That way, I'll have 3 times this is -6 plus 6. That'll zero out this entry right here. Okay, so I'm going to leave row 1 alone. And this is A here. And then for row 2, so I have 3 times this will be -6 plus 6, 0. 3 times this will be 9 plus -9, that's 0. 3 times this will be 3 plus -3, that's 0. 3 times this will be 3a plus this. So this entry right here is going to be 3a plus b. Notice there. So now we take a step back. Would this system have a solution no matter what value we choose for a and b? And the answer is no. Because of this second row here, there are many values of a and b for which this system is inconsistent. For example, well, let me write this. That's worth putting in writing. So this system is inconsistent. There's an N here. For many values of a and b. Of a and b. For example, let's suppose that a is equal to 1 and b is equal to 1. If a and b are both 1, then this entry right here will be 4. And this row 2, the corresponding equation would be 0 equals 4. So an inconsistent system. So because there is no pivot in row 2, once we reduce this matrix, so that's why you have that shortcut in the theorem that says the columns of a matrix will span Rn for an n by n matrix if there's a pivot in every row. Because when there's not a pivot in one of your rows, like we had here, then you're going to have some combination of the entries of your vector over here. And that you're going to have a false statement for many values of whatever your unknown entries of the vector are. So because this system is inconsistent for many values of a and b, the answer here is no. The columns of this matrix do not span R2. One other thing before I end this video. So suppose that we row reduce this and there was a pivot in every row. So suppose we had some 2 by 3 matrix, same setup, but what if it row reduced, let's just make something up, to 0, 0, 1 instead of 0, 0, 0. Then say we augment that with our a and b, and let's suppose this became 3a plus b again. Well, now, for any value of a and b, there would be a solution to this system. Because you'd have, okay, 1 equals 3a plus b. Well, there are infinitely many solutions to that equation. You can pick any value you want for a or for b, and then solve for the other unknown. And so the system would have a solution for any value of a and b in that case, and so the columns would span R2. In this case, we did not get a pivot in every row, and so the columns do not span R2.